Hello students, I bet you can't guess who this is. Correct, it is your professor, the nerdy but consistent Dr. Mink. And welcome to the second lecture of 2 for Chapter 5, Functions for All Subtasks. In this lecture I will be covering the materials from sections 5.3, Using Procedural Abstraction, 5.4, Testing and Debugging, and last but certainly not least, general debugging techniques. Of course, you should have read sections 5.3 through 5.5 in your textbook before reviewing this lecture and/or trying any of the accompanying exercises. Let's get started. Section 5.3 focuses more attention on using procedural abstraction. We'll continue to talk about the black box analogy and information hiding. It is a very useful concept, especially in the arena of reusable code. This should be a review for you. Functions should be designed so they can be used as a black box. And when I look at a function declaration in a program that a student has written, I should not have to look at the details of the body of the function in the function definition. I should know everything I need to know to use that function. I should know if it returns a value, what is the data type of the return. If it's a void function, I know it's not returning a value. I should know what types of arguments I'm passing to the function, whether they're call by reference or call by value. So I should not have to look at the definition. The declaration and the accompanying comments should be sufficient. In other words, the details of how the function performs the task is abstract to me. Here's a new concept for you. Function calls within functions, or in other words, functions calling other functions. Within the body of a function, you may call another function. Probably makes sense that the called function declaration must still appear before it's called, or it'll fail. And one other rule is that functions cannot be defined in the body of another function. Here's an example of a void function named order. It has 2 parameters, both integers, and both call by reference parameters. And within the body of order, if n1 is greater than n2, it calls the function swap values, and it swaps n1 and n2. This would sort them ascending. So swap values is called if n1 and n2 are not in ascending order. After the call, they're in ascending order. Here we have a fully coded solution for us to review. Notice right below the include IOStream statement, there are 4 void function declarations. Notice in main, there are only 3 void function calls. The function swap values is only called from within order if a certain condition exists. You're going to have to forward to the next slide to see the code for that call. So let's stop and move to the next slide, and I'll finish this explanation. Here we see the function definition of the void function named order. And it's a very simple function. It looks to see if n1, the first formal parameter, is greater than the second formal parameter, n2. And if that's true, then it swaps the two values. It calls swap values. And you can see above the function definition for order, the function definition for swap values, which we've seen before, and it actually changes the values because they're called by reference parameters. It changes the values of the two arguments that are passed to it. It swaps them. The author next presents pre- and post conditions. This is a structured approach to writing the documentation for function declarations. A precondition states what is assumed to be true when the function is called, and the function should not be used unless the precondition holds. The postcondition describes what happens or the effect of the function call. It tells what will be true after the function is executed, obviously when the precondition holds. If the function returns a value, that value is described in the postcondition, and changes to call by reference parameters are also described in the postcondition. Here we apply the structured approach of pre- and postcondition to the declaration for the swap values function. The precondition, variable 1 and variable 2, have been given values, so they have to have been declared and initialized. The postcondition, the values of variable 1 and variable 2 have been interchanged. Here we use precondition and postconditions for the declaration for the Celsius function. The Celsius function, if you recall, returns a value. It's a double, and its argument is a Fahrenheit temperature as a double. So the precondition, Fahrenheit, is a temperature expressed in degrees Fahrenheit, and the postcondition returns the equivalent temperature expressed in degrees Celsius. So this is a very structured approach to help you with the black box analogy, to make your function declaration black box compliant. It forces you to think of all the preconditions and the postconditions and makes the declaration more readable, easier to understand. Here the author presents the use of preconditions and postconditions as the first step in designing a function. And you specify what a function should do. Always specify what a function should do before designing how the function will do it. Use of preconditions and postconditions helps in the design process. It helps to minimize errors in the design process, and it minimizes the time wasted writing code that doesn't match the task at hand. Over the next few slides, we'll take a look at a case study called supermarket pricing. So the problem definition, or the requirements as I call them, determine the retail price of an item given suitable input. There's a 5% markup if item should sell in a week, 10% markup if item is expected to take more than a week to sell. So 5% up to 7 days changes to 10% at 8 days. Input is the wholesale price and the estimate of days until the item sells, and the output is the retail price of the item. There are 3 main subtasks in the supermarket pricing program. We need to input the data, compute the retail price of the item, based upon the input and the requirements that were mentioned in the previous slide. And then we need to output the results. We're going to implement each of these subtasks as a function. And notice the use of call by value and call by reference parameters in the following declarations on the next slide. First subtask will be a function named getInput. It will be a void function, and it will have two arguments: a double, call by reference, formal parameter, and an int, call by reference, formal parameter. Those parameters will be named cost and turnover. The precondition: user is ready to enter values correctly. The postcondition: the value of cost has been set to the wholesale cost of one item. The value of turnover has been set to the expected number of days until the item is sold. Now the second function, price, uses, well, it returns a value, so it's not a void function, it returns a double, and it has two arguments, or two formal parameters. Their names are cost and turnover, and they are a double and int, and they are called by value reference parameters. Precondition: cost is the wholesale cost of one item. Turnover is the expected number of days until the item is sold. And the postcondition returns the retail price of the item. Now notice we don't want to change the wholesale cost of the item or the turnover, or the expected number of days for which it will take to sell. So those are called by value reference parameters. Here we have the function for generating output. It is a void function named giveOutput. It has three arguments, three formal parameters: a double named cost, an int named turnover, and a double named price. Precondition: cost is the wholesale cost of one item. Turnover is the expected time until sale of the item. Price is the retail price of the item. The postcondition: the values of cost, turnover, and price have been written to the screen. So this is going to have cout statements and not return any value to the function or the main program from which it's called. And because it has call by value parameters, it won't change anything. Notice how minimal main becomes when you use top-down design and subtasks implemented as function calls. In main, you're declaring wholesale cost, retail price as doubles, and shelf time as an int. You call getInput with wholesale cost and shelf time. You call retail price equals retail price equals a call to price with the arguments wholesale cost and shelf time, and then giveOutput generates the output, returns 0, program is done. The implementations of getInput and giveOutput are very straightforward. So this slide focuses on the development of the price function. Here's pseudocode for the price function. If turnover is less than or equal to 7 days, then return cost plus 5% of cost. Else return cost plus 10% of cost. There's only two scenarios. We're going to represent the low and high markup as constants, so they cannot be changed, and also a constant int called threshold, which is 7. Now We move forward to coding the body of the price function. It's rather straightforward, especially after developed with the pseudocode. If turnover less than or equal to threshold, return cost plus low markup times cost, else return cost plus high markup times cost. Next, we'll take a look at the complete program and a dialog. Because of the length of this program, it has to be displayed over 3 slides. I apologize for that. It gets a little clunky, but we'll do the best that we can. This is the first of 3 slides for display 5.9. This code is available to you in the web study timeline, so you can certainly download it and see the entire program and page up and page down, or scroll up and scroll down, I should say. We'll walk through it. You've got your standard startup statements. You've got your declaration of your 3 constants, low markup, high markup, and threshold. And then you've got a function called introduction. The description of the program is written on the screen. It's very simple. And then you've got the declarations of the 3 functions: get input, which is void, price, which returns a double, and give output, which is void, using the precondition and postcondition framework that the author presented earlier. And then main becomes a very, very slim program. You declare a couple variables: wholesale cost and retail price as doubles, shelf time as an int. You call introduction, which I'll show you in a minute or two, introduces the program. Then get input will provide initial values to wholesale cost and shelf time. That's why they were called by reference parameters in get input. They're declared in main, but we need to change them if we're going to initialize them within the get input subtask or function. Then we have the function named price, which does return a double value, so it's on the right hand side of an assignment statement. And finally, we have a call to give output and the 3 parameters or 3 arguments that are passed to that function. Now I'm going to stop recording on this slide, and then we'll go and take a look at the rest of this program. Hold on for just a second. This slide shows all of the function definitions for introduction, get input, give output, and price. I don't know that I would have, personally, that I would have created a function to introduce the program name and its function, but I guess that's a style preference. You can see the use of call by reference parameters and get input, and the use of call by value parameters and give output, which just sets the formatting and outputs the output of the program. And then you see the call by value parameters in price, which is a function that returns a value, a double. And last but not least, you see a sample dialog from a run of this program. Not much to explain here. If you followed the last 2 slides, this is all rather expected. Here we have some suggestions on testing the program after it's first implemented or coded. You want to use data to test both the high and low markup cases and focus a lot of attention on the boundary condition, where the program is expected to change behavior or make a choice. In this particular case, 7 days is a boundary condition. So the recommendation is to test for exactly 7 days and test for 1 day more and 1 day less. So I would run this program with input of 6 days, 7 days, and 8 days to make sure that you're hitting the correct conditions for all three of those scenarios. That concludes section 5.3, and the author leaves us with some questions to contemplate. Can you define a function in the body of another function? What do you think? I say no. And that would be a good bet. Can you call one function from the body of another function? Of course you can. We've done that. Can you give preconditions and postconditions for the predefined function's square root? Think about that one. Let's move on to the next section in this chapter. The last two sections in chapter 5 focus on testing and debugging techniques. And these are very good recommendations that the author makes and very useful techniques he presents for testing and debugging functions and programs in general. Let's take a look. Each function that you develop should be tested as a separate unit. Testing of individual functions helps you to find mistakes within those functions. The author presents a term, driver programs, and we're going to delve into that in a second. Driver programs are small programs that allow testing of individual functions. Let's take a look at what a driver program is next. In this slide, we'll look at a driver program that tests a function. Function name is f, and f adds two numbers, x and y, and returns the sum. Very complex function. Just kidding. Here's what the driver program to test that function would look like. I have some code here, and you can see the function f takes an int x and an int y, and it returns x plus y. Rather simple. So we could write a very simple driver program that tests the function f. And it's simply, because it returns a value, we could use them as an expression. See out, sum of 2 and 4 is f, with 2 and 4 as arguments, and L. And you could go on and on and on and on and test as many values as you felt is necessary. This is called a driver program. It is a program designed just to test a particular function. Here, let's review what we've discussed so far. Each function developed should be tested as a separate unit, not as part of a call from main, etc. Testing individual functions helps to find mistakes within those functions, and driver programs allow testing of individual functions outside of the program they will be called from. Once a function is fully tested, it can be used in the driver program to test other functions. We'll take a look in a second at a function called getInput tested in a driver program in program 5.10. Hold on one second. We'll look at that next. Here we have a driver program developed for the sole purpose of testing the function getInput. And you'll notice that it has a do-while loop that allows us to continue testing with new values over and over again until we're satisfied that we're getting the desired output from the function, and then we can opt out. Here is the second half of that program, basically the definition of getInput had to be added to the second page along with a sample dialog that allows you to continue by selecting Y for yes at the end when it asks you to test again. And this is very useful. You can continue to input values and know the anticipated results that you should get. And if there are boundary conditions, check all of them. And this is a very useful technique in testing a function. Here the author presents a new technique for testing functions called stubs. When you're testing a particular function and it calls another function that has not yet been tested, you use a stub. You're probably thinking, well, what is a stub? We'll get there. A stub is a very simple version of a function that usually just provides values rather than performing the intended calculation. Stubs should be designed as very simple as possible. And you must have confidence that they will perform correctly. So you may have to determine, given certain values, what the function being called will return, and instead of have it perform those calculations, just return those values. Next, we're going to take a look at program 5.11, in which a function price is used as a stub to test the rest of the supermarket pricing program. Hold on just one second and we'll get to the coded implementation. Here we have program 5.11 from your textbook, and I have to apologize. It's too long to fit on one slide, and the majority of the details we'll be discussing, the stub, etc., are on the second slide. So we're going to have to go back and forth, but you'll see the function declarations of all the functions, and in this particular scenario set up by the author, they're all fully tested except for the function named price. And the author is going to use a stub in place of price's function definition, or the body of the function. So you'll see price returns a double, and it returns a double, which is the retail price of the item based on the cost, the wholesale cost of one item, and the turnover expected. So I'm going to stop recording, and then we'll go to the second of two slides for this program, and you'll see the stub and how it's implemented. Here is the second half of that program, and instead of having a fully developed price function that performs that calculation that we saw earlier, we're simply going to return a value of 9.99. Not correct, but good enough for us to test the rest of the functions and the main program. And you can see a sample dialog at the bottom of this slide where retail price equals $9.99. It's a known value, and it's adequate enough for us to test the rest of the program and get output. And the author leaves us with one last rule for testing functions. He calls it the fundamental rule for testing functions. I get a little tongue-tied whenever I say this, but I'll try it anyway. Test every function in a program in which every other function in that program has already been fully tested and debugged. Got that? I hope so. It's not written in the most explanatory way, but you want to test each function separately in a program, and you want to make sure every other program in the function that is related to that function has already been fully tested and debugged, especially if it provides input. Its output provides input to the program being tested. That concludes section 5.4. The author leaves us with some questions for contemplation. Can you describe the fundamental rule for testing functions? We just went through that. Can you describe a driver program? Yes, a driver program is written specifically to test a function. I prefer to use or to include a do-while loop in a driver program so I can continue to iterate the testing with different input values and check them against the anticipated output values. Can you describe and use a stub? A stub is a stand-in, if you will, for a stunt double, for a function that has yet to be fully implemented and or tested. And typically, a stub just returns a value that can be used as opposed to performing the actual calculation that the function the stub is standing in for will ultimately perform. The last section in Chapter 5, Section 5.5, is somewhat of an overview of general debugging techniques to make sure that you understand the application and the importance of debugging functions and programs. It is a critical part of coding. If you are not good at debugging, you are not good at coding. So we will get good at debugging. Let's see. On this slide, you have some very, very good debugging technique suggestions. Stubs, drivers, test cases, as described in the previous section, are all very useful tools. When debugging a program, keep an open mind. Don't assume the bug is in a particular location. I've seen many, many instances where students, well, I've done this, are focusing on a particular function thinking that that's where the error is, and in fact it's not. Now, this next one is huge. Don't randomly change code without understanding what you're doing until the program works. This strategy may work for the first few small programs you write, but is absolutely positively doomed for failure for any programs of any complexity at all. And if I can add to this, don't change more than one thing without rerunning the program and analyzing the impact of the change you made. Minimize the number of variables that you're dealing with. Don't go in and change 3 different lines of code before rerunning the program, because if you don't get what you want or what you expected, then you've got 3 variables to explore. If you had changed one of those variables and ran the program and determined that what you did was correct, then you could move on and change the second. But if the first one is changed and you run the program and it's incorrect, well, think about this. That could have been incorrect, and the second change you were going to make might have been incorrect, and the third change might have been correct or incorrect. It doesn't matter, but by that time you're so confused. And it's also a good idea to show the program to someone else. Work together with other students that are in this with you and bounce ideas off them. I can't tell you how many times I've written a program and I'm sitting there trying to debug it, trying to get the correct answer, but I've been looking at it and it looks correct to me because I've written it and I've been looking at it so long, and I'll actually walk away. Sometimes after looking at it for an hour and not being able to find where my error is. I'll walk away for a minute, go eat dinner, take a walk, whatever. Come back and have a fresh perspective and immediately see the problem that I couldn't see before. Happens all the time. Always check for common errors. Local versus a reference parameter, the assignment operator versus the equivalence operator. This is a very common error. Just the other day I was helping a student debug a program in which he had a for loop, and in between the three statements in a for loop goes a semicolon, and he had a comma. And I don't know why. I know that a semicolon goes there. I looked at it, I glanced at that part of it, and I wasn't thinking that it was the structure of the for loop that was a problem. The output wasn't generating correctly, but the program was running, and later we found that both of us had inadvertently not noticed that the syntax of the for loop was violated by using commas instead of a semicolon. Very, very simple error, but we looked at it for, I don't know, maybe 10 minutes in class. Localize the error. We're going to look at program 5, display 5.12 and 5.13, and show you a bug in the temperature conversion program and how we use cout statements to find that bug. Hold on one second. Here we have a program that converts Fahrenheit temperature to Celsius, and at first glance it looks fine. But when we enter a temperature in Fahrenheit of 100 degrees, we get a temperature in Celsius of 0 degrees. Well, 0 degrees in Celsius is 32 degrees Fahrenheit. So we have a problem. Take a close look. It's a rather simple problem. Take a close look. And over the next slide, we'll use this problem as an example of how to troubleshoot by breaking apart the actual function or formula to calculate Celsius from Fahrenheit and find out where the problem is. Let's take a look. In this next step in the debugging process, we're going to comment out the original lines of code in the program that calculated the conversion from Fahrenheit to Celsius. And then we will add cout statements to verify each part of the calculation to see where the error occurs. So we declare a double conversion factor equals 5 divided by 9, and then a double temp Fahrenheit equals Fahrenheit minus 32. So we break that calculation into two parts, and then we cout Fahrenheit minus 32 equals temp Fahrenheit, and then we're going to have to go to the next slide to see the rest of this, so just hold on just one second. Continuing from the previous slide, we cout conversion factor equals, and then conversion factor, and then Celsius equals conversion factor times temp Fahrenheit, because that was the original formula, but we broke it down into components that would be better analyzed. So here we run the program again with these debugging couts in there. Enter temperature in Fahrenheit, 100. Fahrenheit minus 32 equals 68. So that checks out. Conversion factor equals 0. That does not check out. Can anyone tell me why? Raise your hand. Oh, I forgot. You're listening to this virtually. It's our old friend, integer division. 5 divided by 9 is an int divided by an int. So it's going to truncate the fractional component, and it will return 0. We need to cast the numerator or the denominator using static cast, or we could simply put 5.0 divided by 9.0. 5.0 divided by 9 would suffice. But this debugging technique allowed us to isolate the problem being the conversion factor, the 5 divided by 9. Use the debugger. Debugger is a tool typically integrated in a development environment that allows you to stop and step through a program line by line while inspecting variables. You can do that in the debugging menu in C++. You can step into and step through a program line by line and see the variables and the values they hold. The assert macro is another useful feature included in the C++ library. You need the include statement, assert, and then assert, and then a Boolean expression. If the Boolean expression is false, then the program aborts. We'll take a look at this in the next slide. Hold on just one second. Here we have a fully coded example that uses assert. In this particular scenario, the denominator should not be 0. So you see a line of code in the middle of this function called Newton square root assert, n greater than 0 and number of iterations greater than 0. If that's false, the program terminates. Not only have we concluded section 5.5, this is the conclusion of chapter 5. And the author once again leaves us with some questions to contemplate and to determine if we in fact understood the concepts, techniques presented in section 5.5. Can you recognize common errors? That's a rather general statement, but I hope you can. Can you use the assert macro? We just covered that in the previous slide. Debug a program using cout statements to localize the error. If you're having problems with that, I can help you. If you find a specific example of a program where you'd like to use cout statements to localize the error, send it to me, bring it to me in class, we'll work it. Debug a program using a debugger. I'm sure I've gone over that in class. The debugging menu on C++ has lots of tools. The one I prefer is, one I use most frequently is to step into and step through your program. Thanks for listening. Have a great day.